Yeah. Hello, show. That per line or? Oh. Something went wrong. 2 to the power 252. I'm not really getting it. 0, 1. Hmm. This does not make any sense. Oh, sorry. Baja. What the heck is going on then? Oh, I think I know what it is. I think I know what it is. Right. So, is this a straight line from 0 to 2? Yes, it is. 2, 1, a half, a quarter, 1/8. The only thing I have to do now is work away these straight lines until they are 0, and then we have the answer. Let's first look at the number itself. 2 corresponds with 1/16, and 1 corresponds with a quarter, and a half corresponds with 1. So that's kind of the square root of 1 over WE. But this in itself is the square root. So it's just, if I divide this number by WE, it's probably as easy as it sounds. So let's not take the square root. Divide by WE. Nope. I guess that's more like it. Now they're all on top of each other. And this is minus this a quarter times the square of this horizontal thing. Beautiful. A sinus. Wow, who would have thought that? Look at the numbers here. This is 10 to the minus 10 to the power minus 12. So it's almost 0. And then the for WE is 16, which is quite big, I guess. The error is the cosine. Unbelievable. Where does that come from? Okay, I call this 0. If you leave out the last one, I mean, you want to see noise, right? So I think that this 0 here, this is the actual noise, and this is something special, which I don't understand, but it's funny. Let's try running to 4. See if we can see that noise. Yes. Round off noise. 2 to the 10 to the power minus 17. So it's like exact. Well, cute little differences here. Green is up here and blue is down there. Something seriously goes wrong apparently for larger weight ratio errors. These are just floating point round-off errors using long double. So quite interesting. You have no idea how difficult this integral is. So I'm numerically calculating the integral. If you ask Mathematica, it has absolutely no clue. It has double no clue. If you ask a simpler version, you get a formula like a page long or something. In the end, it's really simple thing. Now I have to put all of that into G. How to do that? Okay, something horribly wrong with my music. No. What I'm currently returning, this thing is just returning the offset at BE0. Sorry, I have to take care of my music. Started singing, can't think when I sing. Then the music is too loud. Okay. So if BE is 0, then this is correct. Correct being 0. So yeah, you can see that. If this is 0 and that is 0, then we push 0, which is what we want. Okay, so we have 0 equals this. And that means that it equals minus that. And now we divide by WE. And then G equals G1BE plus this, right? Just G to the other side. G plus that, where this is equal to G. And I'm currently returning exactly that, so we have to add this to the return value. Let's see if that works. G integral. BE is the bias ratio, bias error, sorry. WE is the weight ratio. Now G is exact, so now I can just subtract it and then it should be 0. I did it wrong. And I was just stupid to erase it. I'm gonna guess it's a minus sign. Yep. There's still something off, right? Before we had it all down 10 to the power 17. So for small WE now, the error is well significant-ish. So something is still a little bit off. Strangely enough, but what? No, I don't know. I don't know. Just a little bit less good. Maybe first divide and then multiply. It's trying one thing. No, it doesn't do anything. Yeah, I don't know. I mean, 10 to the power 16 minus 16 is still good, of course. It's just peculiar that it is suddenly not as good as it was. No. Okay. Now then, I think I have now the complete integral, ng integral, which is, let me also add here an assert. Almost equal. Not G1, this is not G1BE. It's the whole thing. This is GWEB. Oh, here's this already there. We just assert that it is equal to G within the epsilon position. And it is, otherwise it would have asserted. Okay, I wanted this to be a function of where's my G? Oh yeah. So that. I'm not using bow. I think WE is literal. Why am I calling WE still? I renamed it. Wait a minute. I'll call it a weight ratio. Should call it WR. Maybe even replace it with weight ratio. So I'm calling it a WE. Let me call this weight ratio. Let me think. So the BE runs from -1 to 1. Probably should check that also for much larger values. Well, let me start with checking what happens if I run it from -4 to 4. Damn. It's no longer within the position that we want. Plot it in the graph anyway. Oh, it's that thing. That's really something super weird going on with 16. Very interesting. Yeah, I have to skip that one, I'm afraid. So also 1/16 is it's pretty much further off than the rest. This one is more parabolic in nature than the sign is that the other one showed. Okay, 10 to the power minus 15, that's still within my epsilon, so I could turn on the assert again. And apparently it works. It's not clear to me what exactly bias error is now. I guess I can't see what it is here. I have to look at it here. It will be, but then that gets its meaning from the fact that I pass it here to the integral. Let me rename BE to a bias error. So it's defined by what this thing is doing. And then it's just the offset that we pass through the sigmoid function. So you have u times the weight ratio plus whatever the bias error is. Which means that it is equal to I guess this so I'm calculating this integral and that integral. separately. And then this is the weight ratio. So after multiplying with weight ratio, we add that value that send the bias error. Yeah, definitely. So that's the same thing as I have here. So this whole thing is the bias error. And then we can fill that in. Is being the same thing with the weight ratio being 1, which is this formula, which I worked out here. No, I worked out here. Oh, what? Okay, now I'm confused again. Should be this one, but it's the bias is 0 here. So I think I gave the wrong name. Shit. Okay, I'm calling this, and that is the perfect calculation of the numerical calculated integral, which we do here. But then for a bias error of 0, yeah, so the bias error is 0. In this function with just one coordinate has the bias error at 0. So the naming is wrong. G1BE is actually oops, weight ratio. No, any fool, right? So the G weight ratio 0 is that. Bias is 0, and then we add a bias to it. Subtract it. Yeah, this one is correct. I don't have a separate formula for that here, I just calculated it. Right, G weight ratio 0. That is then this one or that one. I like this notation better, so I'll copy this. There's that one, and then minus a quarter. So the bias error times the bias error. Minus. Divided by 4 the weight ratio. Good. Took a week, but now I have the formula. Okay, almost there. I didn't need to minus this, but yeah, well, yeah, nah. Let me see, the G comes in here. I'd like to have something that is 0 when you fill in the optimal stuff. I think. Well, it doesn't matter at all, of course. But it's just a constant one. Okay, let's say shall I write it down one more time? Everything. Nah, I don't like duplication, so I would just have to copy paste a few things. But in the end, I did already said that before, I think. This. Yeah, I start with a loss, I think. That was the minus. And there's no reason to have a 4 here, I guess. Great. I sure hope that a few things are going to drop out here, because obviously we don't know the WA. A is the weight. A stands for actual. So the actual weight and the actual bias, we don't know those. But they're in this formula. And then we hope that they just drop out at the moment that you take the derivative. For sure, though, the derivative is going to be only 0 when W1 equals WA and B equals BA. So let's maybe, yeah, it's partial derivatives. So I mean, it's two. We have two variables, so I just have to work with two partial derivatives, right? Right. Where's my partial derivative notation thingies? If I have them at all here. No, I don't think I have partial derivatives here. Just sigmas. Is this oh, small font. I was working in the normal font, not the YouTube font. Jorge asks, how good would you say you are in linear algebra, statistic, calculus, etc.? Well, university level, I guess. I did physics. I think I'm pretty good at linear algebra because it's kind of how my brain works, as it were. I think that's easy stuff. But yeah, no, I mean, I'm definitely not comparable with mathematicians. But I know my way around. I forgot what I need. I think we need that, and then something with W also. TW. Just a loss function. This, we need this. Maybe I should look at the final formula that I need. I already forgot. Delta is xz. And then we just use delta, and then that gives me the next xi. And here delta is used again. And xi is z minus t, but that's already a derivative of the loss function. I'm using this, basically. It's the inputs, isn't it? Derivative of the loss function relative to the inputs. Huh? No, wait a minute. This is the initial xi, isn't it? No, this is the initial xi. That's the derivative of the loss function. Should look for the first time I defined this, I think. So the xi of L plus 1 is My memory is bad, I say then, because I already forgot all the details of what I wrote down in this readme. Well, it almost looks like Chinese now. When I wrote this, I understood it. It was easy. I did something else for 2 weeks or even 1 week, I think. And it's already, what is this exactly going on? I think I would understand the code better, and I have the feeling I already translated this into code. So maybe I should look at code. And hopefully find there. I think in the neural network I have already an implementation of this. Something with Xi. Calculate the initial Xi value. Yeah. This is DLDZ, where L is the loss function, Z the outputs. Weights bias times input. Yeah. Oh the heck! I'm gonna go through the whole README, and as a viewer, you should be happy about that, I guess. To refresh my own mind. Each layer has one weight matrix, accompanied with one gradient matrix. That is the same shape as the weight matrix. Consider the last layer of a neural network with n inputs and m outputs. It has inputs x, a column vector of size n. the weights matrix W with shape M times N, M rows and N columns, and a bias B, a column vector of size M, and an activation function A of V. For example, A could be the sigmoid function. I think what I'm now created is the combination of the sigmoid function and the loss function. So I called it a loss function. Actually, the activation function is already included. Oh, we're not there yet, I guess. Example, A could be the sigmoid function. Output Z is the output of the activation function. The result applying the activation function element-wise on V. So V is the result of W times X plus B, I guess. Here, anyway. The layer also has a loss function if it's the last layer. For example, the loss function could be the mean square error function. 1 over m times the sum over all outputs of the squares of the differences of the prediction and the target. Where ti are the elements of a t as function of x. The target for z for a given x. The loss L is a scalar and it's given by L is some function of the activation of the weight matrix times the input plus the bias. Where A is applied element-wise and L combines all elements of A into a single scalar value. It is efficient to append the bias vector as an extra column to the weights matrix. I'm still a little bit in doubt about that, by the way, because why is not everyone doing that otherwise? And append the one to the inputs vector. This is the same effect, but gets rid of the bias vector. So from now on, we add the bias vector as the last column here to the weights matrix. And then an extra one to X, which are the inputs. And now we can just talk about V as WX instead of plus B. And then the loss function can be calculated in 3 steps. First you multiply the weight matrix times the input. And then you throw that through the activation function, and you throw that to the loss function. And I think I combined those two. I'm pretty sure though, even because now see, I don't have everything yet. My formula does not have an X at all. A single adjustment of W is done by gradient descent in the direction that the slope dl dw is the steepest. So we adjust the weight matrix and the bias included by subtracting small times the gradient of L with respect to W. Zup. Where delta W means delta with subscript W, LaTeX notation. And that's the gradient of L with respect to W. which is the matrix consisting of the partial derivatives of L by relative to each weight. I can calculate this and then I can calculate this. And that is exactly what I need, isn't it? Alpha is just the learning rate. So if I have that value, I can update my W. Who needs X? Okay, here I did step by step an example of what is in this link here. This is a small neural network with 2 layers. So we could calculate the V by doing that multiplication. And I filled in what the website said that I used as initial values. Apply the activation function. And that was the first layer. So then we have to do the second layer, and then I needed a new alphabet. So we just renamed everything. Theoretically the same thing, it's just not W times X, but now it's Q times Z. And then activation function and the loss function. Yeah, we should not have had a loss function up here, right? This is just directly the activation function. Z is the output of the activation function of the first layer. That's what we use as input for the next layer. And only at the end you apply the loss function. What I did in the other README is 100% pure mathematics about a single neuron. So it's not generalized yet. It's just a single neuron, so single layer. It's even a lobotomized neuron because I removed one of the weights. I thought the math was hard enough already. Well, this is pretty generalized already. Let's see, at least at the end of this README. So we can apply the chain rule. So this is again the gradient of L with respect to the weights. But we have to calculate them using the chain rule. Because we only know these 3. And not directly the gradient of L as with respect to the weights. But in my case I do. So I think we can just skip that then. Let's see, this is the next layer. The loss function. The different gradients. This, if you do this like this, I mean, this is was for me for understanding. I just filled in, you know, chain rule stuff, and then you get a tensor with a 3-dimensional tensor. But that's a super waste of CPU and memory because it contains mostly zeros. So I worked that out as like this is how the math works. But then we end up with so many zeros and even duplicate values, like you can see here. And then again there, and the rest is zeros. And here you have a lot of zeros, and these are the same. Oh, that's the same thing. Oh, sorry, it's the same matrix. that then in the end you say, yeah, okay, but I can get the exact same effect by doing something else. And then we end up with formulas that I got at the end. This is just still filling in. And still the three-dimensional tensors. Generalization. I don't know, I skipped the point where I said you can do this faster. Auto cheat. So now I do it again, but then in general, so it works for any layer. And then without example values. And then, oh, that's the end already. So I did get to the conclusion that you can work with a xi and a delta. And then this is basically the whole back propagation. If you go every layer that you go backwards, you do this loop once. Ding, 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 ding. Super fast. But yeah, no, it's maybe I went too fast here. I don't know. Oh yeah, it is. Instead of doing 3 tensor multiplications, we can note that effectively this is actually equal to an delta 1i xj, where xj is the jth output of the first layer, and the delta 1i is a characteristic of the ith output neuron of the first layer. And then you get matrix multiplications with the or tensor multiplications with the dimension less. But here you can see something in the formula, but it's actually the derivative of the sigmoid activation function. So if you use something else, another activation function, then this formula even changes. I think I did kind of generalize that more later. This is still the derivative of the activation function. Maybe I should have written that out. So the delta is actually the change of the loss function as function of the output of the activation function. That was what Z was. That is the input of L times, I think this is then dz dv, where v is the output of the matrix multiplication and z is the output of the activation function. So the whole thing is the dl dv then, right? Can we find that back somewhere? It's not exactly, I think. It is this. It's a row vector. That if you multiply this row vector with column vector, then you get the gradient matrix. But I don't think I need a delta. We can just go straight to this. And then we're done, because that's the only thing we need. Yeah, see. So we update the weights with the learning rate times delta of this layer I times xj. And you can wonder what the hell is delta. Well, delta is it comes from the xi, and the xi comes from the xi of the previous layer, or the next layer. If you go backwards, here we go. It's the previous layer, but this whole thing, delta x, is this. Delta x as a whole is simply the derivative of the loss function with respect to the weights. And that is only true, I guess, for the last layer, or when you go backwards, the first layer. Okay, this is with one layer, that is true. In the end, of course, you want to know, let's say if you have 3 layers, you do first the last layer, and then you go to the middle layer. Then also for the layer in the middle, it's already the case that you want to minimize the loss function. So we need to calculate the influence of the weights of the current layer, which does not need to be the last layer, on the output, the actual output. And that is something that is encapsulated in the delta, so the delta is what we propagate backwards, so that we can calculate this. But okay, I think I'm happy with. We're going to calculate that. And we have nothing to do with x. But now in this case, I have a very simple weights matrix. It exists of W1 and B. So we're going to split it up in W1, and then we have the same thing for the derivative of B. So let's calculate those. Now, what is the derivative with respect to W1 of this thing? Do I have to calculate it? I could calculate it, but maybe Mathematica can do this. It sucked like majorly on the other stuff. I'm going to ask it. I never used this before, and this is just a trial that I temporarily have, and it is probably derivative. Here's derivative. Oh, it opened it in the browser. The derivative guess as you derivative, every percent's a derivative of function. Oh, that have one argument. Very unclear as usual. I believe they say you can do all the partial derivatives at once, but I'm not sure whatsoever. Differentiating n 1 times with respect to the first argument. What? And 2 times with respect to the second argument, and so on. And how does it know the arguments? Because then in the example they don't even give, they don't even use derivative. They do it here, but now it's suddenly a -2. What? I guess we just guess and then try it out. What about, I want to know the derivative of x squared. No. Instead of an arrow, it just repeats what you said. So happy. This is not what I wanted. I can call it a function maybe. Oh, I need 2 of those. Okay, let me try that again. So like that. And then say what the variable is, I guess. And then put function in front of it. Nope, still nothing. Just repeats what you say. Function. Oh, I forgot the extra things. Wait a minute. Not only function has brackets, but you need 2 brackets for the derivative itself. Now we get 2x. Oh, that worked. And then this is just the second derivative, I guess. So we get 2. Yeah, so that we don't want that. And then can I add, say, plus 3x plus 7? Yeah, that works. What about make that a variable? And that too. It's also worked. Oh, great. So that it is a partial derivative because, well, a is just treated as a constant. Now what happens if I add another one, because I have 2 variables, then what happens? I think this is just repeating what I said. So I didn't get it. So maybe I have to say x is the first variable and say a is the second. And now I get a 1. Not sure if that's what I want. Nah. Nobody gets this. Maybe remove that. Unknown attribute, so no. Well, we'll just do it in 2 then. So it doesn't get that one. That one works. Then we're going to fill in our thing here. Or let me switch to W. That is then my W1. And the formula is I can do the pi squared, right? Pi squared divided by 3. Times W divided by WA. Does that work? Not sure. Let me use A. single. Can you make variables of more than one character? Maybe it would think that it is W times A. If I do WA. That seemed to have worked. It repeats a constant, pi squared divided by 3, and then we have the derivative here as 1 over A, and that becomes minus A over W squared. Yes. And then we have a plus of a B minus, yeah, well, BA, let's call that C then, times W divided by A, all squared divided by W divided by A. I had expected a logarithm. Is that a good thing, that there's no logarithm? Maybe that's a better way to write it. A times W. That's interesting. I guess I just multiplied top and bottom with WA. Yeah, if you multiply this top and bottom with WA, you get WA squared divided by the two W's. And here top and bottom with W1. So you end up then with W1 squared plus WA squared divided by WA times W1. and the 3 still stays. So that would be the last one. Pi squared, a squared plus w squared divided by a times w and divided by the 3. And this one is then, yeah, the 3 cancels, and this is just multiplied with a squared top and bottom. So you get b times a squared. Nou ja, yeah, yeah. So we multiplied with a squared, so inside you multiply it with WA. So you get BA or AB minus, this was a C, W. No, why not also write that down? Yeah. Anyways, that's quite a mouthful here. Can you use out22 as a verb? Totally. Full simplify out22. No, nothing to simplify apparently. I like that. Just W's W there and there. But hardly. Yeah, well, we have a problem, obviously. Um, Marida, hello. What about studying? Or do you already know everything? This is a problem. The derivative depends on the actual weight and the actual bias, which I don't know. Right, great. Yeah, I think I have to think longer about this. I probably have to work away these constants. Replace them somehow with the target data and the target or something. I don't know. I'm completely stuck suddenly. I mean, it's a fact that if I could calculate this, then it would be a nice, how do you call that? A nice bottom that you can find with the gradient descent. But I can't calculate it because it has variables in it that I don't know. Did I then approach this wrong? Suppose we have the normal shit. So WX, X is the input. And then we take the activation function of that. Let's write it out. To the sigmoid activation function to yeah, okay, I'm gonna, I don't know, I have to think about this for a long time again. I was so happy that I found the integral, and then it turns out that it's not immediately very useful. Like, literally didn't have targets. I must have a target somewhere up in the beginning. What the hell happened there? I only had 3 hours sleep yesterday. Got a bit insomniac guy, I think. Can't really think straight. I think I wrote a program that literally like generated input data. Yeah, this one. This generates points, coordinates, and color according to some hidden distribution. And they're stored in XP and YP. Well, I have two of those. The green ones in one array and the other ones, the red ones in the other array. There's nothing used. They are not used. I'm just printing them. Right. Okay. I'm gone. I'll think about this offline until I have an idea again how to continue. Okay.